Welcome to Chapter 3, which is all about calculating probability. Probability, simply stated, is just the chance of an event happening. So throughout the chapter, we are going to be calculating the probabilities of different events using different strategies. And some of those strategies are content that you learned in Chapter 1 and Chapter 2. Let's first talk about 3.1. And in 3.1, what we're going to do is just talk about how do we calculate basic probability and some of the ways that we can apply basic probability. Let's first define what an event is. An event is just a collection of outcomes that satisfy a specific condition. For example, if you were throwing a standard dice, which has 6 sides, and our event was the probability of throwing an odd number, the collection of outcomes is 1, 3, and 5. And what we should say is those are the favorable outcomes. That's what we want to happen. The number of sides that we have, that's our total number of outcomes. Our event is this single event here. So we have one event, we have 3 favorable outcomes, we have 6 total outcomes. Well, how do we put that all together? What we do is we use this formula down here, and this formula is going to be super important. We're going to talk about it in all of the sections of this chapter. So probability of an event is usually expressed as a fraction. We have usually, so I'm going to talk a little bit about the other ways that we can express it. But to start, we're going to talk about a fraction. And the way that we're going to find the fraction is by taking the number of favorable outcomes and dividing it by the total number of outcomes. So favorable outcomes would be what you want to happen. Total number of outcomes are all of the outcomes that are possible. So if we take our event above, we could see that our number of favorable outcomes would be 3. Our number of total outcomes would be 6. And so our probability of throwing an odd number would be 3 over 6, which of course reduces to 1 over 2. A little bit of notation. So when we want to calculate the probability of something, what we do is we put a P, and then we put a bracket, and then we put the event inside the bracket. So if I just wanted to call that event E, that notation just means the probability of event E happening. So for this case here, the probability of throwing an odd number would be 3 out of 6, or 1 over 2. So we can express it as a fraction. We could also take those fractions and always change them to a decimal. And when we do that, here's what we're going to notice. We're going to notice that the probability of any event is going to range from 0 to 1, which means anytime we take our fractions that we've calculated, and if we change them into a decimal, those decimals are always going to look like 0 point something. Now, if we got the probability to be 0 exactly, which is rarely going to happen, what that means is that event that you are finding the probability of will not happen. That event is impossible. If you calculated a probability and you got exactly 1, what that means is that event is certain. It is going to happen. Now, that's rarely going to happen in this chapter, that we're going to get a probability of 0 or a probability of 1. It's going to be somewhere in between, 0 point something. However, we can say that if an event is closer to 0, so if we get something like 0.001, then that's pretty close to 0, which means the probability of that event is low, the chance of it happening is low. However, if we get a probability that's close to 1, like 0.99, that's pretty close to 1. So while it might not happen, there's a pretty good chance of that event happening. Now, I just want to say that sometimes we are also asked to find the probability as a percentage. and sometimes probability is given as a percentage. So just keep in mind that if our probability was 0%, that means it's impossible. If we found our probability and calculated it to be 100%, that would be certain. So again, our percentages are going to be somewhere in between 0% and 100%. And as we go through the chapter, we'll talk about the different forms going from fraction to decimal to percentage, but just keep in mind that those are the different ways that we can express probability. Let's talk about theoretical probability. Theoretical probability is the probability that is calculated using math formulas. And more specifically, the math formula that we're talking about is the one that we learned above, that the probability of an event happening is equal to the number of favorable outcomes divided by the number of total outcomes. So probability based on math theory. That is in contrast to something called experimental probability. An experimental probability is the probability based on a specific experiment. So let's say that you're going to do an experiment, and in your experiment, you're going to flip a coin 10 times and record the number of times you land on heads. In this case, you land on heads 3 out of the 10 times. So the probability of landing on heads would be 3 favorable outcomes out of 10 total outcomes to give you 3 out of 10. Well, that's quite a bit different than the theoretical probability. Theoretically, we would say the number of favorable outcomes is 1 because there is 1 head on the coin. The total number of outcomes is 2 because there are 2 sides to the coin. So experimental probability and theoretical probability are sometimes a little bit different because especially when the experiment has a very low number of total outcomes. Flipping a coin 10 times is not very many. What we would find is that in experimental probability, the higher number of total outcomes, the closer it is to theoretical outcomes or theoretical probability. But just know that theoretical probability is the probability that we are going to be using throughout the course. The last thing we need to talk about before we can do a couple of examples is a fair game. So let's define what a fair game is. A fair game is a game in which all the players are theoretically likely to win. What does that mean? That means that the probability of winning is exactly the same for each player. So if you are asked to determine whether or not a game is fair, what you need to do is find the probability of winning for each player and then compare those probabilities. If all the probabilities are the same, it is a fair game. If the probabilities are different, it is not a fair game. And sometimes if it's not a fair game, you're also asked who has the advantage. And the person with the higher probability has the advantage. Now that we've done some theory and some vocabulary, we are going to do a few examples. Here is number 1. The spinner below is spun once. Rank each scenario below from that which has the greatest probability to that which has the least probability. So we need to find the probabilities of all those events, A, B, C, and D, and compare those probabilities to each other. I'm going to go ahead and I'm going to look at the spinner. I notice here that the spinners have 5 equal spots. So that tells me right away that our total number of outcomes for all of these probabilities is going to be 5 because there's 5 equal spots on the spinner. So the denominator for each of these is going to be 5. What I have to do now is I need to look at each possibility here and decide the number of favorable outcomes so that I can calculate the probability. Let's start with A. A is spinning a factor of 12. So let's have a look on our spinner and see which of these are factors of 12. 1 is a factor of 12. So is 2. So is 3. So is 4. But 5 is not. So for A, our number of favorable outcomes is 4. Our total number of outcomes is 5. So we're going to write the probability of A is equal to 4 over 5. Let's have a look at B. B is the probability of not spinning a factor of 12. Well, okay, if 1, 2, 3, and 4 are all factors of 12, 5 is not. And that's the only one on the spinner that's not a factor of 12. So for B, we have 1 favorable outcome, still 5 total outcomes. So the probability for B is going to be 1 out of 5. Let's have a look at C. C says the probability of spinning a multiple of 2. So again, let's have a look at our numbers on our spinner. 1 is not a multiple of 2. Multiples of 2 are counting by 2. 2, 4, 6, 8, and so on. So 2 is a multiple of 2, 3 is not. 4 is a multiple of 2, 5 is not. So I can see that for part C, we have 2 favorable outcomes, 5 total outcomes. Probability of C, 2 over 5. D, spinning a prime number. So our prime numbers are numbers whose factors are only 1 and themselves. Let's have a look. So 1 is not considered prime. 2 is a prime number. 3 is a prime number. 4 is not. 5 is a prime number. So for part D, I can see I've got 1, 2, 3 favorable outcomes, still 5 total outcomes. So the probability for D is 3 out of 5. What's nice about these probabilities is they all have the same denominator, so it's very easy to compare them. That's not always going to be the case, but we'll talk about what to do when we have that. So I can compare these right away. So the greatest probability is going to be one that has the greatest numerator, the greatest number of favorable outcomes, and that is A. The next one would be D, then C, then B. From greatest to least probability, same in this case as the greatest to least favorable outcomes. Let's look at the next one. Question 2. Consider each game below and decide if it is fair. If the game is not fair, state which player has the advantage and explain why. Okay, so we have Angela and Mark, and they are each tossing a 4-sided die numbered 1 to 4. And then what they're going to do, they're each going to roll, and then they're going to add up their dice. Angela wins if the sum of the 2 dice is 4. Mark wins if the sum of the dice is 6. Otherwise, neither wins. All right, so you'll see here that we have a nice chart drawn for you here. And what we're going to do is we're going to actually draw out what all the possibilities are. So this is what we call a sample space. And we're not going to do this every time, but for questions like this, it's quite handy. A sample space just shows all the possible outcomes. So it gives us a great way of calculating the denominator for our probability. And it also is a great way to see what all the possibilities are so we can see how many favorable outcomes there are. So I'm going to let this here be Mark's dice. This up here is Angela's dice. And what we're just going to do is find all the possible sums. So if Mark rolls 1 and Angela rolls 1, the sum is 2. If Mark rolls a 1 and Angela rolls a 2, the sum is 3. If he rolls a 1 and she rolls a 3, the sum is 4. And if he rolls a 1 and she rolls a 4, the sum is 5. So you get the idea. So we could go ahead and put all the other sums in here. Okay, and just go ahead and fill those all in. 3 plus 3 is 6. 3 plus 4 is 7. 4 plus 1 is 5. 4 plus 2 is 6. 4 plus 3 is 7. So there are all our possible sums. Now, some of the sums repeat, but they come from different dice rolls, so they are considered a different possibility. So what I can see, again, right away, that our total number of outcomes, in this case, is going to be 16. So our denominator for each of these is going to be 16. Okay, let's have a look at Angela. So we're going to look at the probability that Angela wins. So I'm going to put in here, probability Angela wins is going to be, so she wins if the sum is 4. So let's look here. I see a 4 here, and here, and here. So she has 3 outcomes out of 3 favorable outcomes out of 16 possible outcomes. So that is the probability that Angela wins. Let's have a look at Mark. The probability that Mark wins. So Mark wins if the sum is a 6. 1, 2, 3 6s on there as well. So 3 favorable outcomes out of 16 possible outcomes. So let's compare those two probabilities. Are they the same? Are they different? Are they different? And we can see pretty clearly that they are the same. So because the probabilities are the same, we can quite clearly say that this is a fair game. Probability of winning for each player is the same. Great. We're going to have a look at example B, and we're going to use the same strategy as we did with example A. We are going to write out the sample space and use the sample space to help us calculate the probabilities. The difference is that the sample space here is going to be a tree diagram, which was different than example A where we used a chart. So Eddie, Larry, and Tony each toss a coin. If all 3 coins land as heads, Eddie wins. If all 3 coins land as tails, Larry wins. Otherwise, Tony wins. So let's start with our tree diagram, and we're going to start with our first toss. And that first toss could land on heads or tails. So with that single toss, we have 2 possible outcomes, heads or tails. Then we're going to toss the second coin. Now, we're not sure right now what happened with the first coin. We just know that there's 2 outcomes. But with the second coin, it could either land on heads or tails if the first landed on heads, or if the first landed on tails, the second could also land on heads or tails. So what happens now is we have 4 possible outcomes. Heads and heads, heads and tails and heads, tails and tails. Third coin is tossed. And what happens is we add on some more branches to the tree. If the first lands on heads and the second lands on heads, the third could land on heads or tails. If the first lands on heads and the second lands on tails, the third could land on heads or tails. If the first lands on tails and the second on heads, third, heads or tails. And if the first is on heads or tails and the second on tails, the third on heads or tails. So you can see what happens now is we have 8 possible outcomes, or 8 branches on the tree. And reading down the branches, we can see what the outcomes are. So heads, 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 tails, heads, tails, heads, and so on. So what we have here is our total number of outcomes is going to be 8. We have 8 branches on our tree, 8 possible outcomes. Okay, so let's go ahead and calculate the probability for each player. And we're going to start with Eddie. Okay, so the probability that Eddie wins. Okay, Eddie wins if all 3 coins land on heads. I only see 1 branch that has all heads on it. So his number of favorable outcomes is 1. Total number of outcomes is 8. So probability for Eddie winning, 1 out of 8. Let's have a look at Larry. Probability that Larry wins. He wins if all 3 coins land as tails. Well, I only see 1 branch that has all 3 being tails. So 1 favorable outcome for Larry, 8 total outcomes, probability 1 over 8. So right now, it looks like the game is fair, but we've got 1 more player. What is the probability that Tony wins? Well, all it says is otherwise Tony wins. Well, that means that if there's 8 branches total here, if Eddie wins on 1 and Larry wins on the other, that leaves 6 branches left, and we can see them. Here's 1, there's 2, there's 3, there's 4, there's 5, and whoops, there's 6. So the probability that Tony wins is 6 out of 8. Well, that shows us right away that not all the probabilities are the same for each player, which means this is not a fair game. And we were asked above that if it was not a fair game, we have to say which one has the advantage and explain why. So we can see here that this is not a fair game. We can also say that Tony has the advantage since her probability is higher. So there's our first intro to probability and how we can use it to decide if we have a fair game.